Hello everyone, welcome back to this lecture on spectroscopy. And a few minutes ago we discussed the first and the oldest technique for mid-infrared spectroscopic imaging, which is what's called FTIR imaging. And uh, this technique uses like some old components. For example, the source of light, mid-infrared light, is basically a black body radiation. It's like something like like light bulb type of a device. So there are several innovations which have happened in the recent past 10, 12 years or so, which have made new kinds of imaging systems possible, which allow us to do much better than FER in different ways. Okay, so one of the some of the problems of FTIR imaging are it takes long time to collect the data. It's relatively the intensity of light is relatively low, and the detectors, for example, are limited to camera, even like a cell phone camera will have megapixels, right, millions of pixels on it. But infrared, mid-infrared, it so happens that it's very difficult to make these sensors, the camera type sensors. 128 by 128 or 256 by 256 is like a common size. It's like its number of detectors is very few. So these are some of the practical problems with FTIR imaging, and because you take an interferometric approach, so therefore you collect the entire spectrum, which is a good thing if you want the full spectrum. But let's say you just want to measure a certain like just 4 different wavelengths or 10 different wavelengths of at spectral positions of wavelengths. So then it's a like this FTIR approach like is not the best way. So there are new approaches which can be useful, which gives you much faster and data if you just want data at a certain set of wavelengths. That's one of the like those are some of the problems that we are like the new instruments address. And the other thing is you get a lot of data. So if you want to collect all the data and do some data processing, it takes a long time. I mean, like it takes computationally, it's a very you need algorithms like GPUs and other algorithms which do heavy which the computation is quite intensive, and it's you need some dimensionality reduction and other things to make it tangible or to make it usable. Okay, so another problem is high dynamic range. So if there is one big peak and a few small peaks, the big peak dominates, and so there are problems in the way you collect data. So all these kind of problems, and there are other issues with respect to water absorption and few other things. Because of these kind of problems, people have been trying to figure out how to improve FTIR imaging and get new approaches to mid-infrared imaging. So what in terms of technology is new? So these are the new things which are just in the past 10, 12 years, which are kind of have revolutionizing the field. So you have the availability of new types of lasers. For example, you have called quantum cascade lasers. So these are much more powerful in terms of intensity per unit area. And there are super continuum lasers and there are comb lasers. There are different types of lasers which have come about in the past few years, which allow you to do much better than the old methods. Okay, so there is technology has improved, so you can use the new technology to build new kinds of better devices faster and easier, like higher quality data. And so based on these kind of lasers and other detection methods, there are different instruments which people have built. So I'll talk about a few of them. So some are QCL, quantum cascade lasers, also called QCLs. So these are single wavelength type of lasers. I'll get to the details in a minute. But basically, if you can use this kind of a laser, you don't need to collect the full spectrum. You can just tune the laser to one wavelength and another wavelength, only wavelengths of interest. Let's say in breast cancer, you figured out that you first collected full spectrum data, and you realize that only say 20 of the wavelengths are important for diagnosis. The rest of the thousand wavelengths are not useful. So you don't need, like in FTIR, you have to collect the full spectrum always. But with QCLs, one of the advantages is you can just collect only the 20 different wavelengths, or whatever wavelength you want, you can collect data at those positions. So that's much faster than collecting the full data. So that's one way in which some approaches, these approaches like become more efficient. Another is there are other issues, for example, resolution. So mid-infrared light goes from about 2.5 to 12.5 microns in wavelength. Okay, so this is lambda. And so lambda by 2, 2NA, or let's say for like simplicity, lambda by 2 is basically the resolution you can get typically from a microscope. That's the limit of resolution. What's called the diffraction limit is the best resolution you can get from a system which uses the wavelength lambda. So if it's say visible light, right, like say 500 nanometer, which is greenish color light, then 500 divided by 2 is 250 microns, right? So basically you can get 250 microns. I'm sorry, 500 nanometers, 250 nanometers. I apologize. 250 nanometers. It's 0.25 microns. That's you can see things of that size. But like if you have 10 microns light, then you can see 5 lambda by 2 is 5 microns, right? The resolution is 5. And so basically it's factor of 10 to 20 worse, like it's much bigger size than if you use visible light. So the question then is, like that's a disadvantage of infrared imaging. You get much worse resolution than, just because the wavelengths are longer, you get worse resolution, which is called the diffraction, because of the diffraction limit of light. And so the question then is it possible to actually get like visible resolution images with spectroscopy, with infrared like contrast? So can you actually get best of both worlds? So like best of the visible and best of the infrared. Infrared, what does it give you? It gives you the chemical composition, right? It gives you the spectrum. That is very valuable. But visible gives you better resolution. So photothermal imaging is a way of actually combining the two in such a way that you get best of both worlds. And I'll talk about that I'll go into the details in today's lecture. So let's start with the first frequency, the QCL based imaging systems. So if you just want to, so instead of collecting the full spectrum, this bit in yellow here, if you, instead of getting the full spectrum of light, the entire spectrum like you get with FTIR image, you can just choose a certain set of wavelengths and collect data at only a few wavelengths. The thing is, the QCL, quantum cascade laser, can give you that. And so the advantage of quantum cascade lasers is that it can tune across a wide range. So typically you can tune across this range of wavelengths. Now you have like lasers which are available for this as these range, like other wavelengths as well. But so this is called the molecular fingerprint region. The fingerprint region. So it's like a fingerprint. So different molecules have different kind of peaks, and so it's very useful part of the mid-infrared spectrum. So if you make measurements in this region, you can identify a lot of molecules in the chemical composition of samples. So and QCL, in fact, because it's, so imagine this is like sort of visible light is something like 0.4 microns to 0.7 microns, right? Like roughly. But this, imagine it's 2.5 to 12.5 microns. So this range of wavelengths is so much long, like so much more, right? So the number of wavelengths or the range of wavelengths is a lot more. And in that sense, the mid-infrared covers a much broader spectral range in some sense. If you look at it in terms of wavelengths. And the reason, the consequence of that is you can't use just one laser. You actually, for covering this range of wavelengths, you actually use 4 different lasers which are combined together. You can't like sort of the one laser is simply not enough. One QCL is simply not enough. So a laser, quantum scale laser actually has 4 lasers inside, which combine together in some way and get light out. And these are tunable. So you have a laser at one wavelength, you can tune it to different wavelengths and kind of choose where you can uh, ask it to emit light at that wavelength and then just sweep across, for example, or keep it at parked at one wavelength and make measurements. So you have some control over what you can do with these kind of lasers. And it's a high intensity light source in the mid infrared region. So you can get good data. So you can basically, so typically instead of sitting at one point getting a spectrum, sitting at one point getting a spectrum, which is how FTIR typically works. So what you can do here is get a full image at one wavelength, change the wavelength, get another image at another wavelength. So there are like kind of different ways. You can also get a sit at a point and get a spectrum. That's also okay, but it's typically much faster to get one image, then choose a different wavelength, get another image, and so on. So there are different. It gives you flexibility in terms of how you want to collect the data. So like if depending on your application, depending on what you want to do, you can collect data in several different ways. It allows you to build new kinds of imaging systems which utilize this quantum cascade laser, and you can get much better that kind of data in that sense. But still, if you just use a quantum cascade laser and nothing else, then you are still limited by the diffraction limit. So the resolution you can get is still kind of limited. That is where photothermal imaging comes into the picture. Okay, so what the big advantage of photothermal imaging is that you can get a spatial resolution of something like half micron, which is basically comparable to what you get with visible light, but you also get spectroscopy at the same time. And so it takes the best of the visible microscopy, best of the infrared microscopy, combines the two. In fact, it's a super resolution method. So what is a super resolution method? Typically, a microscope lambda by 2 Na is the resolution limit, diffraction limited resolution from any microscope. If you can get images that have better resolution than this, it's called super resolution. And photothermal can do that. Not only can it do that so when lambda is like 5 microns, 10 microns, like in that range, it can give you 0.5 micron resolution, which is a factor of 10 better than like in just regular infrared microscope. It can it can give like much higher quality data than previously possible with any kind of infrared imaging system. Okay, so that's the essential kind of advantage. So the way I'll go into a lot of details of how it works. So let me just give you a big picture idea of what the basic principle is. So you have mid-infrared light. So it's a system in which mid-infrared light is falling on a location, focused onto a small point in the sample. At the same time, you have a visible beam exactly going along the same parallel path, incident at the same point. Both the visible and infrared are incident at the same location at the same time. Okay. Now, what happens when visible infrared light can be absorbed, right? So, if let's say in a sample there is some molecule or some group of molecules which absorb infrared light and expand. So, or which absorb infrared light. So, what happens when light gets absorbed? Like energy is deposited. When energy is deposited, there is like heating. When there is heating, there is expansion. When there is expansion, there is a change in the refractive index or the height, both. The combination of height and refractive index change, right? So whenever there is so this is called the photothermal. So light falls on a sample, it gets absorbed, it expands a little bit. And so why is there a visible light incident? Visible light, what it does is, it measures how much of a height change or a thermal expansion there is. So it's like one excites, one laser, the infrared laser excites that region, The other laser is a probe which measures the region. Okay, so it's what's called a pump probe architecture, where this combination of excitation and measurement happens, like the excitation happens from the mid-infrared, measurement happens with the second laser, and this way. So imagine if the light is not absorbed at all, then there is no change in the signal. So light from the visible uh, falls on this particular location. Let's say it doesn't get absorbed, then there is no change in, like, whether the infrared is incident or not, there is no change. So turn on the infrared, you will get some signal, like, so light, visible light scatters back here. That you measure it at a detector. You measure some detector intensity. To turn off the turn off the infrared, you get some detector value. Turn on the like infrared. If there is no change in the sample, there is no change in the detector value. But if there is an expansion, then the light scatters in different directions. So there is a change in the visible probe detector signal. So if there is more of absorption, there is more of a change in the. So you have on and off. You take the difference. There will be a big change if there is a lot of absorption. If there is no change, there will be zero signal change, right? So that's the essential principle of photothermal imaging. If like there is photothermal excitation, if there is absorption, proportional to the absorption, there is some amount of expansion, and when there is expansion, there is a change in the signal that you measure from the visible beam. So visible is acting like a probe to measure the changes that are happening. More the change, more the absorption. Therefore, it's proportional to absorption at that wavelength. You change the wavelength, do the measurement, change the wavelength, do the measurement, you get a full spectrum. That's the idea. So this is the essence. Cut a long story short, what kind of data that you get? This is what's called bone marrow sample. So this is actually something which I did in my research lab with my instruments in my lab, and from like a collaborator at a hospital. So this is what's called bone marrow is the part of the bones inside that is where blood cells are made. I don't know if you know this, but the red blood cells, all the different blood cells in your body are made inside the bones, in the middle of the bones, in what's called the bone marrow. Okay, and this is images of that. This is if, say, for example, there's a mutation inside the bone marrow, then that results in blood cancer. Different kinds of blood cancers are depend on the problems inside the bone marrow. So that's why bone marrow imaging is part of one of the projects I'm working on. Okay. So we got a sample of bone marrow from the collaborator, and what we see is that if you do the QCL based imaging at the hospital, you get like this kind of image from inside the bone. But you can see this is from our instrument in my lab. So you can see with the photothermal effect. So you can see that this image, if you want to zoom in here and look at the comparison between the two, it's much higher quality, right? Like you can see that this is much higher resolution than this. This is blurry, like blobby, and this is much more fine grained information. So this is this is the kind of image you can get, high resolution image you can get from the photothermal effect, which is like with diffraction limited QCL based imaging. It's hard to get. Okay, so it's the exact same sample, so it's easy to compare. For so some of the fine details here, for example, becomes just a blob over here, right? So you can see how nicely these kind of areas are. You can see all these things. Bunch of blobs. So there is not enough resolution to give you good quality images, but with this instrument you can see it much more clear. So this is the essence of what is it's capable of. How to use this for biomedical diagnostics and few other things I'll get to in a few minutes. But I first want to kind of explain how the instrument works, some of the details of. So there are not, it's not just one instrument, it's a category of instruments. So they use different ideas. In fact, in my lab, we have used some new ideas as well to come up with new kinds of instruments. So I'll talk about some of these basic like ways in which you can collect the data with thermal principles. Okay, so all of them use some form of this this mechanism. Okay, so you have a mid-infrared beam, which is also called the pump beam. You create a vibrational transition. I mentioned that molecules, there are different quantum mechanical states. So light gets absorbed if it corresponds to a difference in the vibrational transition state. And so when there is a transition, then it goes to an excited state, and then it relaxes. It comes back down over some time. Whenever it relaxes, the energy has to go somewhere. It becomes thermal. Like what is thermal? It's jiggling of molecules. It's molecular molecules like increase in the average kinetic energy of molecules. And then the temperature change results in a size change. There could be an expansion, there could be a density change, and that could correspond to a refractive index change, which an optical probe can measure. It could be probe could measure something related to size and density, or it could measure something related to the refractive index. And there are different instrument architectures which use like each of these approaches. Okay? So this is the essence of, and this gives you photothermal contrast. And if there is a lot of absorption of mid-infrared at one wavelength, then you have a lot of change. If there is less of absorption, there is less change, and therefore the signal is proportional to the absorbance of the at any given spectral location. Okay? That's the basic idea. Yeah. So here, to give you some kind of how to quantify this, I said little bit more, little bit less. Those are qualitative things, right? But there are precise mathematically quantitative ways of saying it as well. What this is saying is amount of energy which is absorbed minus amount of energy that goes out dissipated is proportional to the mass, the peak heat capacity, and the temperature change as a function of time. Okay, so how much temperature changes? If you have a lot of temperature change, it's good because you'll get a better signal in some sense. So if you have a little bit of temperature change, it will be a smaller signal. So that's the idea. That's related to how much energy is getting absorbed. And then, so therefore you can come up with an equation for temperature as a function of time, which has some characteristics. So it increases and then it decreases. So when you turn on the QCL, so what you do is use a quantum cascade laser. You turn it on and turn it off, and turn it on and turn it off. When you turn it on, it increases, and then when you turn it off, it decreases. Okay, it's on, off, on, off. So there is an exponential, reverse exponential increase and then decrease and so on. You might have seen these kind of waveforms in in your electronic charts and stuff, but this is actually the photothermal kind of. This is the process that happens, and this is the kind of measurement you get out of your detector from some photothermal imaging system, for example. Yeah. So there are different ways of making measurements in using the photothermal effect. One is called the dark field method. I shall get to in a minute. But what happens is that there is some length change. Like whenever there is an expansion, the change in length is proportional to the thermal alpha, which is which is called the linear thermal coefficient of expansion, and the original length, and also the change in temperature. So bigger the change in temperature, the more your change in length will be. Okay, and similarly for refractive index, there is some proportionality constant. Bigger the change in temperature, the more the change in refractive index will be. So one method of making photothermal measurement uses what's called the dark field approach, where the detector intensity. So as I said, make a measurement with the infrared on, infrared off. So the delta is the intensity that you measure, and the length change, the refractive index change, and the length change. Okay, So this is with the laser on, mid-infrared on. This is with the mid-infrared off. And so basically you have light is getting light is illuminated from from a cone, like sort of different directions, and what you measure is change in the scattering properties of light. Um, in all different, so as you know, light scatters in all different directions. You have light only incident from some directions. From other directions, you measure the scattered light, and so this is called a dark field configuration. So it allows you to kind of measure these changes much more effectively, change in the overall scattering because of change in length or change in refractive index. So with this approach, you can make very precise, very accurate photothermal measurements. So this is one of the first ways of doing photothermal measurements. Another way is uses interferometric methods. So it uses the interference. So uh, light is incident on the sample. So it's on a maybe there is some beads or something, like some tissue on a glass slide or something of that sort, like some kind of calcium fluoride, some substrate, and you have light incident on it. So you have there is like initially without the light on, mid-infrared light on, it has a certain shape. When you have the light on, there is a small change in shape in the sample. So what you do is make interferometric measurement. So you have, so for interferometry you need the sample arm and the reference arm, right? In this case, the reference arm is basically the glass substrate or the calcium fluoride, some kind of substrate. So one wave comes from the signal, like the sample, another wave comes from the substrate. They interfere with each other, and at the detector you measure the change in the signal intensity because of the interference between the scattered wave and the reference wave. And so this approach is called interferometric scattering contrast. This is very useful to make very sensitive measurements. The reason why it's useful is the signal is proportional to ES times ER. So ES is the field from the scattering, ER is field from the reference. So what happens often is that ES, how much light scatters, is very small. The field that is scattered is a very tiny amount. Say a million photons come in, maybe a few, like 100 or like a few of them just come back out as scattered photons. But the good thing is there is a multiplication of ER times ES. So if you can make ER very big, it acts like an amplifier. It amplifies the scattered signal because there is a multiplication of two numbers. If you make, like you have control over, you can make the ER, the reference arm power, you can make it big. So that way it amplifies the scattered signal. So it's like essentially like an optical amplifier of a certain sort. And so that way, because this cross term is where the face is related to the cross terms that you saw in the previous class. So therefore, you can use this effect and get a much stronger signal because of scattering than you would otherwise get without the reference. So this is another approach to getting a good photothermal signal. The third one, which is the last one I'll talk about, is just using optical phase. So in this approach, it's like you remember the quantitative phase microscopy kind of approach. So it uses something like a quantitative phase or a phase microscope along with photothermal effect, a combination of the photothermal along with the quantitative phase approaches to give you a signal, good signal. So what you want to do is measure the change in phase. So this is called a hot frame, like when light is infrared light is incident. This is called a cold frame where light is not incident. So on and off, and you measure the phase, the difference between on and off measurements, and that will give you optical phase contrast. So there could be a change in refractive index, there could be a change in length. whatever the combination, n times L is the optical path difference. So there is some change in path difference that results in some change in phase, and that phase is essentially what we can measure with optical phase contrast. So this is another way of measuring the photothermal effect, and all these methods give you very good So to some of all the different ways in which you can make photothermal imaging measurements, and these all of these have been built and they work quite well. So here is one of the instruments, the kind of instruments we have in my lab. So which the way it works is infrared light, mid-infrared light. So you turn it on and off and on and off. So this is a pulsed beam, right? Like the pulsing is on and off and on and off and so on. So this is the QCL beam, which is on and off. Infrared beam comes here, and the visible beam is the green color light in this case. They get combined in what is called dichroic mirror. A dichroic mirror is a mirror where it reflects one wavelength and transmits another wavelength. So in this case, it reflects the green laser and transmits the infrared laser. So it's like a beam combiner, and then it both of them are incident onto the sample over here. The sample is put here. This is a part of a microscope. So this is an objective. It's a reflective objective which focuses the light onto a spot, and then only the infrared is absorbed, so it doesn't go through. So if you have a sample here, only the visible light goes through, and there's a photodiode here, which is the detector on the other side. So whenever this is on, you get some signal here. Whenever this is off, you see a change in the signal, and therefore by looking on and off and on and off, you make this measurement and kind of at that frequency of on and off repetition of the QCL, the measurement you see is related to the photothermal signal. So this is the idea. So the other, so people have done this. Not only that, because you have already a lot of the components here, people have also put in what's called a Raman. In the lecture on different mechanisms and light matter interaction, I spoke about the Raman, like different Raman processes, right? Like the Raman scattering effect. So this uses Raman. You can also build photothermal along with Raman at the same time into one kind of an instrument. That's one possibility. Another thing is what's called a wide field. So the first one was point scanning, meaning you take one point, make a measurement, move the point, another measurement, right? So it's one point after the other. So that is the point scanning. You can use a camera-based approach, and the camera-based approach is what? Sorry about that. Sorry, yeah. It's also called a wide field approach. It uses like a wide area at the measurements at the same time. So one way to do it is have an infrared light and use what's called a chopper. So what is a chopper? It's like a wheel where there is a black space, like there is gaps, like there is a kind of, it's like a spokes of wheel. So one part blocks the light, the other part lets the light in, blocks the light, lets the light in, and so on. So if a beam goes here, it goes through. If it goes on the dark part, it kind of cuts off. So basically, if you rotate the wheel and there's a laser beam here, it turns on and off, turns on and off. It's like essentially turning on and off the laser at whatever speed you want, like how many times per second you want. Okay, so this sends the beam in like onto a sample, and the visible light comes in from this direction in this case, and is also incident. Light that scatters back goes onto a camera. You make a measurement. So in this case, it's not one point detector, it's a camera. For on, you have one camera image, off, another camera image, on, another camera image, off, another camera image. So you get a sequence of camera images, consecutive images. You can subtract, or you can do some kind of data processing after you get all the data, so that you can get the photothermal effect. The advantage is at every pixel, like you can get all different, an entire full image. After you do the data processing, you get a full cube of data. At every pixel, you get the kind of photothermal signal. Okay, so that's the advantage of this kind of an approach. So not only that, so with with the phase contrast kind of imaging, you use quantitative phase imaging (QPI) along with photothermal. So this is an instrument which does photothermal, and the way you measure the visible light is the phase contrast microscope. So I already discussed the phase quantitative phase imaging in detail in the previous lecture. But the idea is the essential idea is light comes in just like before. You use the chopper, turn it on and off, and so on. You combine, like you have it incident on the sample, and the visible light is going, and it's also getting modulated. It goes through. There is like basically a grating and a pinhole, which is like all this combined together is basically a part of a phase contrast microscope. And this is a camera. So you get the same kind of images for on and off with quantitative phase, and this allows you, the phase change allows you to measure the photothermal effect. That's the idea. Okay? So going around the same lines, this is the last type of system that I'll show you. This IR is incident on the sample, and then visible, like it's here. The idea is that instead of using a bunch of other objectives and different ways of collecting the data, they've used what's called a mirror objective. Mirror objective is a special type of lens where it's like a beam splitter and a lens combined into one piece. Okay, so it's like a lens. It's a lens where there is a mirror inside. So half the light goes into the sample, the other half goes to a mirror, and light comes back. So it's a combination of a beam splitter along with a lens, both in one single device. You can buy this kind of a device from a few companies, and this has the advantage that it gives you interferometry along with the phase information both in one system. So it gives you much better contrast than some of the other methods. So it's also easier to build, and it has some of the advantages of giving you contrast, good contrast. Okay? So this is also a camera-based wide field approach. So people have built all these different kind of photothermal imaging systems. We also in my lab have built systems. I'll show you some of the data from our imaging systems as well. But this is essentially the landscape of all. This is literally cutting edge. Everything I'm talking to you here has happened in the past 5-6 years. Okay, this is literally at the cutting edge of mid-infrared imaging that I'm talking about. We are these ideas are at the very forefront of what people are doing in today's in this field today. And in terms of what are they using this for, what are the different kind of things that people do? So one thing people have done is shown 3D imaging, and with the mid-infrared, with photothermal contrast, you can do 3D kind of an imaging. The depth to which you can go is not like in OCT where you go millimeters. You can much shallower depth, like 50, 100 microns of depth. You can get 3D information as well. You can get IR imaging, and at the same time you can get Raman images of the same thing. You can get living sort of, this is it's a worm of C. elegans, which is commonly used. So this is kind of actually a the living thing which you can measure with the photothermal effect. And people have done, like even my lab, we have grown cells and make measurements of the living cells using the photothermal effect. So it's actually possible to get very good data on living cells. In FTIR, it was very hard to get living cell data, but with this photothermal system, you can get from living tissue and living cells and living organisms. You can actually get data from that. Another thing is you can get quantitative phase images along with photothermal. So basically, you can get molecule. In one of the disadvantages of quantitative phase is that you don't have chemical specificity. The photothermal gives you the chemical specificity, and that way it gives you much better information, combined information, say of a neuron, You can get details of some neuronal activity. You can get histology, meaning if you have tissue, like which is one of the ways in which people do cancer diagnosis or different kind of disease diagnosis. The doctor puts these chemicals on the, like, takes a part of the place where if there is, say, you are suspected of cancer, they say breast cancer, they'll take a piece of tissue from the suspected region, cut it into slices, put some chemicals on it. These are called 18 hematoxin and eosin. So these are common chemicals that you put. It gives you purple and pink kind of images. The doctor looks at this kind of an image and decides, is this cancer, not cancer, what grade of cancer, and so on. So that's typically how a diagnosis is done. You can get equivalent better images without actually, so you get like without, you'll get this kind of an image, and you can convert it to an image of this sort and give the doctor something which they are familiar with. I mentioned in the previous lecture that, like, sort of, if you give doctors something which they've already seen, what looks like the same thing that they've seen before, it's more easy for them to adopt it in their clinical setting, right? So that's we have people have done this kind of transformation to show images, like, because the chemical information is already there, and without using any extra chemicals, with label-free images, you can get colored images by doing some computational, like doing some machine learning and classification, and like with those some of these approaches. So there are all these lot of different kind of applications, a wide array of applications where you can get lipid, protein, carbohydrate distributions inside and different tissue and so on, where you can see a lot of very interesting things. So the photothermal imaging has a very wide array of applications. It is very useful for both biological and clinical and biomedical and all different kinds of samples. Okay. Sorry. So the next thing, in the next few minutes, I wanted to describe a couple of things which I am doing in my lab, where, like, these are clinical, medical and clinical applications of photothermal imaging, which where my focus, like, I'll talk about some of the things which are at the cutting edge in clinical setting. My lab is one of the few which does clinical samples and with the photothermal effect, and we have made a lot of progress, and I believe we are at the cutting edge of this kind of research. For example, one of the diseases that we are studying is called myelofibrosis. It's a life-shortening complication. Basically, it's like a blood cancer. It is something which leads to blood cancer. It's a problem in the bone marrow where there is a specific kind of, there are what are called reticulin fibers that are growing, and these fibers, so red blood cells are produced in the bone marrow, and whenever there's a disruption in the bone marrow because of there is a mutation or something of that sort that happens, and as a consequence, these fibers start growing inside the bone marrow. And if these fibers grow too much, then the number of blood cells that are produced will get reduced. Not only that, whatever blood cells are being produced, they have some problem which causes, makes it cancerous and so on. So that's the essential problem. And so to give you a sense of how, like one of the features of this disease, if you look at this image over here, the pink is regular bone marrow tissue. The black lights here are what are called reticulin fibers. There are specific type of collagen fibers. So the problem with these fibers is that whenever you have bone marrow in the with these kind of fibers, then it disrupts blood cell production, and this is essentially what causes results in the cancer. And the problem I'm working on with some doctors is that, so until recently, until about 10 years ago, if you get this kind of cancer, you are essentially like there is the chance of you surviving is very, very small. But only just recently have people come up with this new kind of like medicines which are called JAK2 inhibitors. Like JAK2 is a mutation. It's a gene which, and a JAK2 mutation is something which. So there is a new class of medicines which, if you have a specific gene which is problematic, there are medicines which can target some. These are called gene therapies that can target some specific genes, one or few set of genes. JAK2 is an important like JAK2 mutation is an important problem, and so there are JAK2 inhibitors which basically are a treatment. The problem which my collaborators who are doctors figured out was they give this medicine, say, to 1,000 people. 300 of them get cured very well, like sort of they almost show no symptoms of cancer afterwards. But 700, like 70% of the cases, they don't improve. And they don't know why. And what we are trying to do in my lab is to help them figure out why. How to identify the people who will respond, how to figure out who will not respond. And so if they don't respond, then maybe you can try a different treatment. But right now it takes about 2 to 3 years to know if the treatment will work or not. And by the time it goes to by the time you figure it out in 3 years, the person, it may be too late. The cancer might spread too much, and basically, so what we want to do is reduce that to 6 months, or reduce it. If you give the patient a treatment, if it is working, then you want to say yes, this is working, and continue. If it's not working, you want to figure it out, and you want to change the treatment. So that's the goal of this project. And what our scientific approach is to figure out, take a biopsy, take a sample from the bone marrow, and look at this reticulin fibers. And this reticulin fibers, if they are very parallel and ordered in a like sort of like they're kind of they're low in density and they're parallel, then it's kind of improving or lower grade disease. But if they're crisscrossing and dense, then it's high grade disease. In other words, if you can find the orientation of these fibers, map the orientation out, then that's a way of figuring out whether the disease is progressing or not. That's the essential idea. And in order to do that, what we had to do is, we realized the reticulin fibers are about 1 to 2 microns in diameter. So therefore, you can't just use regular infrared imaging because you get a 5 micron resolution. You can't see 2 micron objects, right? 1 micron objects. So but photothermal gives you half micron resolution. So you can see 1 or 2 micron size objects. Therefore, photothermal is a good way to go. Second is that you need a way of figuring out the orientation of these fibers inside. So we actually had to invent a new photothermal method, which not only gives you this, figures out where these fibers are, it tells you the directions, the orientations, so that you know if it's crisscrossing or if it's like parallel to each other or kind of like crossing each other kind of thing. So we invented what is called a polarization sensitive photothermal instrument. So where we add polarization, so you have like light also has polarization, X and Y polarization. So you can use a polarization base, so which instrument which does photothermal, but which also has polarization contrast, which allows you to see some things. I'll get to that in a minute. So we like these are the typical stains that doctors use, what's called reticulin and trichrome stain, and this is a bone marrow. This is the kind of image we get from our regular instrument, and we got this kind of data over here. And so this is the FTIR instrument, and this is the photothermal instrument. And if you zoom in to some of the regions, you can get, so this compared to this has much higher quality data, in the sense, first we just double check that the resolution is much better than the standard FTIR. Not only that, we looked in more detail. So this is so there is a thin fiber over here, reticulin fiber. So if you do FTIR imaging, so this is the full image. Yeah, I'm zooming into a small region. So look at this region of. So I'm zooming into this region over here in this location. Sorry about that. Yeah. So, so this panel over here is FTIR. This is the photothermal. So in the FTIR, because it's a 5 micron resolution, you cannot see the fiber here. But with photothermal, you can see the fiber. So this is proof or evidence that you can, what you could not see with the FTIR old instruments, you can see with the new instruments. And it is useful for medical purposes. And not only that, you do like, so if you apply different polarizations, so if the light is polarized in a certain way, what does polarization mean? So another property of these thin fibers is that at different wavelengths, they absorb light in different ways. So if you have light, say, to give you an example, let's say the fiber is oriented this way, okay? So if, say, the electric field is oriented this way, then it will absorb some amount. If the electric field is oriented perpendicular, it will absorb less at one orientation, more at a different orientation. So this is called the dichroic properties, okay? It depends on the polarization of light. If the light is along, the electric field is along one direction, it will absorb in one way. It will absorb less in the other direction. And that depends on the, for two different wavelengths, this property is different. So what you do is, make a measurement at one wavelength, make another measurement at another wavelength at all these different polarizations. So we made measurements at 0 degree, 0, 45, minus 45. Okay, so 3 different polarizations at one wavelength, 3 different polarizations at another wavelength. So 6 different measurements of data. And so by making these measurements, you get images, full images at both these wavelengths. So this is what we called photothermal, like polarization sensitive photothermal imaging. So this is a paper from about 2 years, 3 years ago. So what we found was that, say, in this case, the fibers are horizontal. The fibers are kind of in this direction. And the polarization is 0. So this direction, polarization is horizontal. Red is very high, blue is low, white is like 0. So high value. So the horizontal fibers give you a very high signal when you have horizontal polarization. And so when the fibers are, in this case, are like this, minus 45 degrees, the minus 45 polarization, this image has a lot of red, which is, it has a lot of high signal, compared to this one where it is like the other perpendicular, which has not so high. Fibers are like this and like this. 0 degrees, which is this, and 45 degrees, which is this. So these two images have high. This image, which is perpendicular, which is in this orientation, is low. Right? So basically, the whole point of all this is, by making these kind of measurements, you can figure out which direction the fibers are oriented. And with this, you can construct an image of this sort, where at every pixel, you can figure out what direction the fiber is going. So this way, if it is parallel fibers or crisscrossing fibers like this, so if it's parallel fibers, it's lower grade disease, and it's this kind of crisscrossing fibers, it's high grade disease, right? So we have a quantitative photothermal measurement of figuring out what the fiber orientations are. With this approach, we can start solving the problem of when is the disease progressing, when is the disease not progressing. In fact, it's a 5-year study where we have, I'll get to ovarian cancer in a second, but basically the point of this project is that we have biopsies at different time points from our doctors, and we'll study them over 5 years and see if we can predict if this patient is improving and the disease is becoming better, or if the disease is becoming like worse or staying the same, then you can make a treatment decision. You can change the medicine that you are giving, and so on, and it will have an important like benefit to doctor, like to the patients at the hospital. Okay? For blood cancers, myelofibrosis. Okay. Uh, how much time do we have? 5 minutes. Okay. Yeah. So the next important problem that we have been working on is ovarian cancer diagnosis. This is another kind of a cancer. So where the current method of doing ovarian cancer diagnosis is that if a woman is suspected of ovarian cancer, then doctor will go and do a biopsy. It takes a piece of tissue from the ovary, and they'll cut a bunch of slices. Each slice they'll put different stains. So H&E stain, nascent trichrome stain, Vimentin, like cytokeratin, CD31, all these different stains. And a doctor who is called a pathologist will look at all these images under a microscope and decide, okay, is this cancer, is it low grade cancer, medium grade, high grade, or grade 1, 2, 3, 4, more specifically. So basically they'll do a cancer, like estimation of cancer. And so this process of cutting into slices and putting different stains and making a diagnosis can like take a lot of time, and also it takes several days to do this. Typically in a hospital, like it takes the time to do all this kind of staining. Our goal is essentially to kind of avoid all the staining and just one stamp like image, like one tissue without any stain. If you just get that tissue, if you put it under our imaging system and press a button, it should do the full imaging at different wavelengths, and then not only that, use machine learning to do a diagnosis of what is going on. Okay, so that's the kind of direction in which we are going. And so basically, if we can do that, then it makes it much more quantitative and much faster. So as you can imagine, the doctor looking at it is subjective. So if one doctor looks at it and another doctor looks at it, because it depends on the person's training and other things, there is a variability. In fact, people have quantified and studied this. There is sometimes a 30% chance that you go from one doctor to the next, they'll change their diagnosis or change what they think is the problem. Okay, so there is a big variability, and the good thing about this photothermal imaging or mid-infrared imaging in general is it's quantitative. If you put the sample in one instrument, take it to a different instrument, you press you do the measurements, they'll be the same data, right? Except for there is noise, but other than that, there is from one instrument to another instrument in a different country, in a different hospital, in a different place. It's precise and quantitative. If you take the same sample, you'll get the same answer. It's quantitative. Therefore, that's a big advantage. There is no subjective variability, unlike in a lot of these. Same thing with staining. Sometimes you leave it for a few seconds extra, the staining quality will be different. So there are the staining is also kind of a subjective process, or at least there can be large variability in the staining as well. So these are the kind of problems which we can address with our photothermal imaging. Additionally, it gives you some kind of information, molecular information, that you can all not obtain with stains. So staining, each chemical, why do we use so many chemicals? Each chemical attaches to a certain protein or certain kind of compound inside the cells. So, but we can use intrinsic contrast. We don't need to add extrinsic contrast agents. We can actually get all this information quickly without the need for all these chemicals which are added. So that's one advantage. That's another advantage. Okay. Yeah. So that's the essential goal of this method. This approach is to develop new methods for ovarian cancer diagnosis, which are better than the current approaches. And so what we have done is basically so we started with H&E data, which is a biopsy, so you always want to compare to what is already done, and this is what is already done, the left side images. and we get data from the photothermal instrument, which looks like the right side, and the FTIR instrument, which is in the middle. And already you can see that the images you can get from the photothermal is higher resolution and higher quality than FTIR, and you can get, I'll show you that you can get data comparable to H&E kind of images. So we did this for and another important thing you always have to remember is if you just do it on one sample or a few samples, it's not enough. You want to do in a statistically large number of patients or number of samples. Otherwise, you don't have statistically robust results. Meaning, by chance, you might have gotten the correct answer. So, how do you ensure that whatever the results you're getting are not just by chance, but because of something important and real in the real world? You do it on a lot of patients. So, in this case, we took 100 different patients and collected photothermal imaging data. And this is at one wavelength, one wave number, gamma at 1 peak, but we can do this at all different, anyway, bunch of wave numbers. So here is the raw data. So this is the photothermal raw data. This is the HD image on the right. What you can see first is just in the raw data, you can see yellow and kind of blue regions. So you can see that there is a good correspondence between the yellow region here and the purple region here. So this is without adding any chemicals. This is intrinsically what are the molecules present. If you look at that, you can see the connection between this. Sorry about that. So there is already a connection in the raw data between what you do with after a lot of staining and everything, but we can see that in the raw data directly with our instrument. Now, the reason it's important is, let's say you use some machine learning to figure out, convert this kind of raw data with not just multiple wavelengths into something which the doctor can see. The problem in a lot of machine learning is what's called the garbage in. Sorry about that. Acting a bit weird. Okay. So garbage in, garbage out feeling. You have to check and double check that the raw data has some chemical information in it, which the machine learning is only identifying what is already there in the data. The machine learning can hallucinate and give you something which is kind of, it can look like convincing images, but it's actually not real. So how do you know if it is actually corresponds to the real world? In the raw data, you see the patterns. So you see that this yellow corresponds to this kind of purple here. So in the raw data, you already see that there is, qualitatively, you see that there is some chemical information in the data. What the machine learning algorithm is doing is just quantifying this, what you see qualitatively. Therefore, you can trust the machine learning algorithm, because especially in diagnosis and medical fields, it's crucial that you trust the answer that you get. And if you use machine learning, if machine learning hallucinates, which is a very common, well-known problem in all kinds of algorithms, it's a very serious problem. You cannot trust it, and therefore it will never be used in the world. Okay, so that's why in the raw data you have to check and confirm that there is actually real information, chemical information, which is there, which is the basis for your machine learning algorithm to give you the correct answer. You always have to trace back and see and make sure that it's identifying something real. You can trace it back to a certain molecule or a certain feature, and that's an important thing you always have to keep in mind. If you want to use machine learning for medical purposes, that's tracing it back to some molecular feature or some specific thing you can point to is a crucial aspect of getting it to work properly and reliably. And I've done this, so we did this analysis of 78 cancer patients, and we got, after using CNNs, we got an accuracy of about 0.98, 98% or so for tissue subtyping, 2 different subtypes of so epithelium and stroma classification. For all these different cores, we got a very good analysis. Not only that, we came up with a measure called the stromal ratio. Okay, so this is basically the ratio of stroma to all other tissue. And so we realize that for normal to grade 1A, 1B, 1C, there is a big change in this number. Meaning, If the tissue is normal, you have some value for this metric. For grade 1A, 1B, 1C, even the early stages of ovarian cancer, this number changes a lot in a statistically significant way. So p-value of less than 0.01. So it means in a statistically significant manner, that there is a change. So this is a way of figuring out if it's an early stage ovarian cancer. This method allows us to figure out early stage ovarian cancer. Okay, and we also did this for cervical cancer. So we took 100 cervical cancer patients, got images, FTIR and photothermal images. We did the same kind of classification. We are at right now 94% accuracy when it comes to cervical cancer detection as well. So I'll pause here for today, but so this is the kind of thing that made possible by with photothermal imaging. So I showed you the principles of how this instrument works and different ways in which you can build the instrument. Once you build it, what can you do with it? You can do different identify myelofibrosis and help doctors into ovarian cancer detection, cervical cancer, subtyping, and so on. So this opens up a world of possibilities in terms of what this can be used for. Okay, let me stop here. Any questions? Any questions about anything we have discussed? Any questions online? So there are several other applications like Alzheimer's, kidney diseases we're working on in the lab. I'm not presenting those things. I'll be happy to discuss some of these projects with you if you're interested. But I just wanted to give you a flavor of some of the kind of things that are like this technology makes possible. Okay.